Standard e-commerce platforms operate on a predictable model. Users browse vast catalogs, add items to a cart, and check out over hours or days. Global entertainment events operate under an entirely different mathematical reality. Look at the sheer density of a crowd at a major stadium tour. For highly anticipated events, the active user base attempting to access the ticketing platform can surge to 100 million daily active users, all converging on the exact same inventory at the exact same moment. During normal operating hours, enterprise web traffic maintains a steady, manageable baseline. But when a flash ticket sale begins, that behavior vanishes, replaced by a sudden, massive concentration of demand. Under baseline conditions, a major ticketing platform processes between 1,000 and 5,000 requests per second. During a celebrity-scale flash sale, that load compresses into a highly concentrated burst, routinely reaching between 100,000 and 300,000 concurrent requests per second. This line graph compares that 1,000 request baseline against the 300,000 request peak. We are looking at up to 100,000 active requests targeting a single available seat. The core engineering challenge here is not caching read-heavy data like event pages or seat maps. The challenge is managing extreme write contention for scarce inventory during a tightly compressed checkout window. Surviving this level of concurrency requires abandoning traditional database locks entirely. The architecture must be rebuilt from first principles to decouple concurrency control from data durability. The first architectural principle of a high-concurrency platform is strict ingress mitigation. A load of 300,000 requests per second must never reach the core transactional engine. To prevent this, traffic is intercepted at the edge using a virtual queue, built entirely on Redis sorted sets. We can see this on this diagram of a Redis sorted set. When a user requests access, the system executes a z-add command, recording their identity and assigning a timestamp score, naturally guaranteeing first-in, first-out ordering. This data structure executes insertions at log-n time complexity, sorting millions of users in sub-millisecond times. Users are then atomically dequeued in batches using the zpop-min command, preventing race conditions during admission. Sorting the queue is only half the problem. Admitting users at a static, pre-configured rate almost always leads to downstream bottlenecks if the booking engine suddenly slows down. This flowchart illustrates an adaptive control loop that monitors downstream stress. It tracks seat contention in real time by calculating the seat conflict rate, dividing the number of failed seat selections by the total selection attempts. The platform targets a conflict rate of 5%. If the rate breaches that threshold, indicating high contention for remaining seats, an admission controller dynamically chokes the ingress batch size, restricting access to minimize booking failures. To keep waiting clients updated on their position, the queue pushes notifications via server-sent events. Because this communication is strictly unidirectional from server to client, SSE avoids the heavy connection handshake overhead required by WebSockets. This adaptive queue operates as a mathematical shock absorber, constantly tuning the ingress flow of users to match the real-time checkout capacity of the backend. Holding traffic at the edge creates an immediate security vulnerability. Automated bots and scalpers will attempt to bypass the queue entirely and hit the booking APIs directly. The system requires a digital passport, a cryptographic proof of entry that is only granted when a user legitimately exits the virtual queue. This visual breaks down the structure of that passport, a JSON Web Token, or JWT. The payload includes standard claims, a unique user identifier, the allowed event resource, and a strict 15-minute expiration window. The queue service generates this short-lived JWT upon admission, minimizing time for token theft. To prevent forgery, the token is cryptographically signed using an asymmetric RSA algorithm known as RS-256, secured by an internal private key. When the admitted user attempts to reserve a seat, their request is intercepted at the API gateway layer before it reaches the backend. The gateway executes a validation sequence, extracting the key ID from the token header and verifying the cryptographic signature against a cached JSON web keyset. If the signature fails or the token is expired, the request is dropped. This handoff instantly rejects unauthenticated load at the edge, protecting the booking engine without spending a single back-end database read cycle. Once inside the booking engine, the system must account for the human variable. After selecting a seat, a user typically takes between 2 and 10 minutes to enter their payment details and complete the checkout. A naive engineering approach attempts to secure this 10-minute intent using a standard relational database row lock. This interface displays that standard approach in Postgres, executing a select for update query on the specific seat row. This command locks the target seat row inside an active, long-lived database transaction, preventing any other user from modifying it. The mechanical flaw lies in the duration. The database must hold this lock open and idle while waiting for slow human typing and third-party payment gateway responses. Apply a massive surge of 100,000 concurrent requests per second to that fragile architecture, and this catastrophic failure is the immediate result. Long-lived transactions require active database connections. When thousands of users attempt to hold seats simultaneously, the database connection pool is instantly exhausted. This triggers a cascading failure. Query contention backs up the web application servers, causing timeouts that eventually crash upstream caching and search indexing layers. ACID-compliant relational databases are built for data durability. Using them to manage temporary intent during a human checkout process guarantees systemic collapse. The architectural correction is to completely decouple concurrency control from the primary relational database. The booking process is instead modeled as an explicit three-state machine: available, hold, and booked. The hold state is managed entirely in memory. This diagram shows a Redis cluster node executing an atomic key-value operation to establish that hold. The NX parameter stands for set if not exists, guaranteeing the key is written only if empty, ensuring only the absolute first request acquires the lock. The PX parameter enforces a hard 10-minute time to live. This provides operational elegance. If a user abandons checkout or a server crashes, the key natively expires, returning the seat to the inventory pool without requiring scheduled database cleanup jobs. Because this lock is managed in Redis, the execution takes sub-millisecond time, entirely bypassing the transaction overhead of a disk-based database. Securing the seat introduces a secondary challenge, communicating that state change to the thousands of other active users viewing the exact same seat map. Broadcasting every single seat update individually generates extreme network CPU load. Instead, the system relies on section-based pub-sub, batching seat updates over 500 millisecond windows. Transmitting a single consolidated delta payload reduces network message volume by up to 99%. Deploying a distributed in-memory lock cleanly insulates the durable database from both the latency of human behavior and the chaos of high-concurrency race conditions. This architecture map traces the complete lifecycle of a user request. Traffic routes through distinct layers, enforcing a strict division between managing ephemeral and durable state. Relational databases like Postgres sit at the very end, strictly reserved for the final, permanent booking ledger. Every step prior to that relies on lightweight, fast-executing mechanisms. Edge queuing controls the volume. Asymmetric cryptography verifies the identity. In-memory locking secures the temporary intent. Enterprise scalability is not achieved by infinitely expanding database hardware. It is achieved by mathematically throttling flow at the edge, locking state in memory, and strictly bounding the lifespan of user actions.